Okay, so I'm going to be going over transresistance amps here. And so to start with, description. Well, what is one? Well, a transresistance amp is a IV converter. And that means that the input is your current, which is I, and your output is V. So what does one look like? Well, a basic IV converter looks like this. And so you see over here you have IDC coming in, and then you have V out over here coming out of it. Okay, so this will be your output over here. This will be your input. So to start the analysis, what you want to do is you want to take a look at your currents, and you want to set some conventions up for how your currents flow in your circuit. For the most part, you just need to be consistent with how you set things up. But other than that, you can arbitrarily make your currents however you want to, but you just maintain your consistency throughout your analysis, and it'll all come out correct. So to start with, we have IN here, VN over here, VP here, and then V out there. So of course we're using an op amp for this. And so our analysis equations are going to be KCL at VN. And what are we going to get there? Based on the convention that is made up here at this node VN, we're going to have IDC equals 0 plus VN minus V out over R. Then that just reduces to, you have VN equals VP, which is ground, and ground equals 0. That helps, reduce this as a first step. So you have your 0 minus V out over R, and then that reduces to negative V out over R, because ground, which is 0, and that's why it came out over here. And the 0 here is simply because if we go back over to the diagram, let's take a look at that. When you go back over to this diagram, what you see is that you have this current going down into the amp, but any op amp, any ideal op amp doesn't have any current going in. So that's why this is 0 here. Okay, so let's go back over here to this. So now we've gotten to this point here where this is simplified to this point. And so we just simply see that the relationship between IDC and V out is negative R times IDC is going to give you V out. So that gives you, as you'll notice here, it gives you a function of V out as a function of IDC. So the simulation setup, if you simulate the circuit and you use the same values that I did, then you'll get the same result. And so what I did was I did a parametric simulation just for two differing values of R. One R is 1K, and then the other at R equals 2K. And so that simulation is going to be swept from negative 1 milliamp to 1 milliamp for my IDC values. And so the simulation result comes out to be this. So this is R at one particular value. In this case, this is at 1,000, and then this is at 2,000. And I'm going from negative 1 milliamp all the way to 1 milliamp. And so next, there is another type of IV converter. It's called a T-network IV converter. And it is a variant of the basic IV converter that uses a T-network to produce higher transresistance gains for a given value of R. So what does it look like? Well, this is the circuit topology. Again, we're using an op amp here, and so we have IDC here, and then V out is at the same point in the circuit. So we've just added on R2 and R1, and this is your T network here. So when you do that, what we want to do is we want to come up with a functional relationship between IDC and V out, and when you do that, of course, in your circuit analysis, you set up your arbitrary current flows, and so I have IN going in here, which is the same as IDC, and I have this coming out here, have that coming out there, and you see how I maintain the consistency. So if I said that current is flowing this way in this branch of the circuit, it must be consistent throughout. And so arbitrarily I just put a current here going this way and a current coming out there. And so these are going to be the two nodes that I'm going to use for my equations. And so to begin with, KCL at Vn. So what we do is we start with IDC equals 0 plus Vn minus Vb over R. Then next we have Vn equals Vp equals ground, which is 0. So right over here where we have Vn, we're going to replace that with 0 because that's the equivalent value of it. That's going to simplify us in our equation here a lot more. So then with zeros placed in there, we end up with IDC equals negative VB over R. Then we rearrange that so that we isolate VB, and we have negative R IDC equals VB. That's going to be equation 1. So next, KCL at VB. That gives us this equation here, Vn minus Vb over R plus V out minus Vb over R2 equals Vb minus ground over R1. And so ground, of course, is 0, so that's going to reduce this part over here, and all we're left with is Vb over R1. Then we split up these fractions here because what we want to do is isolate Vb. So we split the fractions up and we bring Vb over to the right side. These fractions here with Vb in the numerator, bring them over to the right side. Then you have this. Next, again, Vn equals Vp equals ground, which is 0. That's your op-amp virtual short rule. And so we have a Vn here. That's going to be equal to 0. So when we do that, then we have 0 over R, and then that's going to simplify us some more. And we're left with V out over R2 equals VB over R1 plus VB over R plus VB over R2. So we just take out VB, factor it out, and we're left with this, and that's going to be equation 2. So we're going to take equation 1 and we're going to use it in equation 2 to eliminate VB. And so when we do that, we put in place of VB equation 1, which is negative R IDC. We put that there, and then we continue to rearrange our equation. And so when we bring R2 over to the right side, then you're going to have a cancellation here, and it's going to make a 1, and then you're going to have R2 divided by R1 plus R2 divided by R for these two terms here when we bring R2 over and we distribute into these parentheses. So 1 plus R2 over R plus R2 over R1, all of that in parentheses, it's going to be negative or negative 1 times all of that times R times IDC. And again, that gives you a function of V out as a function of IN. IN is going to be IDC. So again, IN is IDC in this circuit. So that's your functional relationship there. And so my simulation setup, what I use for values here is, again, I'm doing a parametric sweep for R at 1K and then R at 2K. R1, I'm going to set that and leave it at 1K. R2, I'm going to set that and leave it at 1K. And then IDC, I'm going to sweep that again from negative 1 milliamp to 1 milliamp. So notice again with R and IDC, it's the same as the last simulation. that I did. The only thing here is that I have the addition of R1 and R2 in this T network. So let's see what our simulation result looks like. And this is what I got. So as you can see, you have higher starting values here as compared to the regular basic IV converter. You have higher values here, and that's what you're supposed to get, because all of that, if you look at the equation, if you go back to the equation, all of that is being increased by having R2 and R1 in your relationship here. So going back over to the simulation result, again, it's higher here and higher there, but again, if you have R at 2 kilo ohms, that's going to be higher than R at 1 kilo ohm, which is this green line here. So R is at 1 kilo ohm for the green line, R is at 2 kilo ohms for the blue line. And so that is that. So that brings this to an end, and that's all I am going to cover in this lecture slide presentation about IV converters. Thank you for watching. Hopefully it was helpful. Have a nice day.